Welcome to our stream. I'm happy to present John Baker. If you have any questions before I forget, please ask them in the comments. So they will be answered later. And without any further ado, well, I will let John introduce himself and begin. Thank you.
Problem. Thanks, Alita. Good morning. Those of you who don't know me, my name is John Baker. I'm a performance nerd. I don't go so much with lofty titles with IBM. I really haven't done anything else, which is why I'm presenting this subject, because I wasn't smart enough to do any programming or to learn enough about databases. But if you want to go into performance, you really just kind of have to know a little bit about a lot of different things. And that's actually what this session is all about. So if you're thinking about a career in this space, I can tell you, if you know Martin Packer, my buddy, he's been doing this for a long time. I've been doing this for a long time. He's going to retire. I'm going to retire. A lot of other people, Peter Enrico's going to retire, and there's not that many of us. So there's lots of opportunity in this space if it's something that interests you. Okay, let's keep moving. Some of you have probably seen this one before. Always fun. 1991 is right around the time that I was getting into mainframes, thinking, what are you doing? This is going away. Maybe this is such a good idea. But it's worked out pretty well so far, as I like to say. So we all know clearly there's lots of demand in the mainframe space. It's just a matter of which role you want to try. I like this one too. You ever go to parties and you're talking to friends and they're so, what do you do for? It's pretty hard to explain to people what you do for a living. You work with mainframes. Maybe just say works with computers. Keep it as simple as that. Keeping our obsolete devices serving the obsolete world as we do. Some of the popular mainframe jobs out there, application programmers obviously need lots of them. If you know COBOL, Java, C, lots of other languages, you can pretty much write your own ticket. System programmer, same thing. Learn a little bit at JCL Rex. If you can write an assembler, boy, oh boy, you're valuable skill. Database admin, like Elisa, if you know DB2, that's useful. Even IMS has databases. If you can kind of work across them. Some of the big shops that run IMS as opposed to relational, it's hierarchical database, kicks. But of course, what I want to talk about today is my job, the performance analyst. And there's lots of ways you could describe it, but the way I look at it is it's really the technical role that actually aligns with business goals. I mean, what is every executive since the beginning of time always been saying? We need to do more with less, right? We need to continue to find savings. We don't cut costs, sounds very harsh, but you just find opportunities for improvement, make things run more efficiently. In our world, that means, can my application consume less CPU, fewer MIPS and MSUs, which contribute to the software bill and contribute to getting more capacity. But at the same time, you've got customers and you want to maximize the experience of the application for those customers. We don't write code. What we do, we balance priorities. One of the things I will say repeatedly about the mainframe compared to, say, commodity server environment, it's a large shared ecosystem, and shared is the key word. In a kind of a commodity server cloud environment, you just throw virtual servers at something because they're relatively inexpensive. There's no one tuning all those individual servers. And you technically could do that with Z. You could say, well, we're going to add more cores, we're going to add more machines, but that's a business decision. That's expensive because They carry a lot of weight, but they're also not free. So again, that quote. Nice quote from Ray Wicks at the bottom. Ray, the late great Ray Wicks. If you're not familiar with him, he was possibly the most talented capacity planner IBM ever produced. He is the core founder of the CP3000 models, if you've ever looked at those. And I really learned a lot from Ray. I miss him. Talking about the intuitions behind the formula, which is important. There's a difference between the formula and understanding what the formula is telling you. And I guess this is where I maybe make the point, because a very, very common question that comes up, especially these days, is, well, can't AI do this? I'm not against AI. AI can do lots of really cool things, but AI is book smart. AI only knows what you tell it, what books you can ingest into its library. It doesn't have intuition, to Ray's specific point. It doesn't possess intuition. It doesn't possess the ability to reason. It doesn't understand the needs of your business. It can say this number is higher than normal. Okay, is that good or bad? Is it a problem? It can maybe point you to things, but it can't quite do the job. Who knows? Maybe someday, but I haven't seen it yet. So if you do want to embark on this path, there's a couple of useful skills that I'm going to go through this morning. And first, might surprise you, is actually communication and judgment, not really technical. Part of your role when you're managing, really this entire environment, executives will want to know, hey, how come this application's slow? Hey, how come our software bill's so high this month? Hey, what do you mean I need this bigger new machine? And you need to be able to communicate in the language of the executives, the application owners, the different roles. So we can understand each other. It's not helpful to be throwing around jargon and things like that. Obviously, you got to know a little bit about Z fundamentals. So I can't write a line of assembler, but I know kind of how the machine works. I know how the mainframe hardware and operating system works. I'm not a Kix or a DB2 expert, but I know a little bit about how they operate and interact together and with the operating system. You got to know some basic math. We'll talk a little bit about queuing theory, utilization, response time, and averages, and priorities, which is always a fun one. If you ask AI what it thinks you should do when an application is running slow, I've pretty much consistently seen it say, well, just increase the priority. Well, how far do you go with that? Do you increase everything? Make everybody importance one? That's probably not going to run very well. So about the communication, first of all, you got to be an interpreter. As I mentioned, there's people that are running the business that speak about, business terms, business success, strategy, deliverable, margin, costs. Whereas we're talking about performance index, dispatching priority, transaction response time. You need to be able to translate, your technical terms, what you observe in the data through your tools into the language of the business. What does this mean to them? That, this particular application has a performance index of 1.5. That's meaningless to the executive. What you want to tell them is that you're not getting the response time you normally get. And then ideally you can explain why. There's my clicker. You also have to be a judge. And this is another thing that's kind of difficult for AI to do. You got to make decisions, which are sometimes subjective in nature. So, fun way to look at that. My colleague Jerry, I'll put this together. I got a good chuckle out of it. Consider two scenarios. So, you might contact an application owner because you're looking at your reports every day with your favorite tools. I use IntelliMagic Vision. Of course, there's lots of tools out there. But you might notice something new. Hey, what's this application? find out who it is, call them up. I see you've introduced a new application to the system. And they may not respond. Application owners are very busy. They're under great demand to produce new features every day. So sometimes you don't get a lot of response. You might say, can you tell me a little more about what this application brings to the company? Remember that role. You are the large shared ecosystem. This is just one application. An average mainframe environment's running dozens or hundreds of concurrent applications. You have to understand a little bit about them so they can get along, if you will, in the giant Z swimming pool. It just needs to run efficiently. Okay. Maybe another scenario, an application owner contacts you. Hey, I hear you're the performance person. I need my application to run faster. Okay, can you tell me a little more about your application? I need my application to run faster. Okay, well, what is your application bringing to the company? There's a lot of concurrent applications in the mainframe here, and we've got to kind of try and balance these roles. I need my application to run faster. Okay, that's often the way some of these conversations go. So what, at the end, in both cases, right? You have to be a judge. You have to make the judgment yourself. It is something that you really got to understand about the role, is that you're deciding of all the dozens of hundreds of applications that may mean, millions of dollars of revenue or loss for the company you're working for. You're literally deciding priorities. You're literally deciding who goes first and who waits. So, in the first example, maybe you'll just put the application to a lower performance service class. It says it needs to run efficiently. You know what? The mainframe runs pretty efficiently, regardless of what your priorities are. Now, if things get a little bit busy, some things might run faster than others, and that's why it helps to set these priorities appropriately. On the right, maybe you're going to put the application in what I called here an unjustified service class. So maybe you're going to give it a higher priority. But when things get busy, that could mean that other applications suffer at the benefit of this. So this is one of the reasons you want to try and find out as much as you can, and you want to contrast and compare the behavior of the applications in your environment. So that is, what sort of SLAs do they need? Like, do you need a half second, a millisecond response time, or is it a batch job that, as long as it's done by 6 in the morning, it doesn't matter? And you want to contrast that with the resource consumption one. Again, is this using a whole lot of CPU? Do you have an application that's maybe using 20% of the resources on the entire mainframe? Now, if that application is responsible for 20% of your company's revenue, that might be perfectly fine. We'd call that a cost of doing business, right? But what if it's only responsible for a very tiny percentage of revenue, yet it's consuming 20% of the resources? This is something that needs to be brought forth. And this is where you need to use those communication skills and talk to the executives, because you're not trying to bash anybody here. But we all know that the mainframe often gets, really bad reputation. But, it's really, really expensive. Well, it's not about the design of the machine. I can tell you, it's the most efficient general purpose computer on the planet. But if you have applications that consume a lot of resources, they ought to be generating a lot of benefits for the company. If they're not doing that, then those applications need to be tuned. There's only so much that you can do within the environment. So in order to do that, you got to know a little bit about the machine. If you know Frank DiGilio from IBM, he likes to, the title he's given himself is Chief of Declunkification. And he likes to use this analogy, I think is a good one, is that today, for example, you have the Martin Packards of the world that I would call mechanics, right? They know everything about every single part in this machine. I'm using the car analogy here. They know all these parts and how they all go together. You don't necessarily need to know all that. But you do need to know how to drive, right? You can't expect some of your monitoring apps or AI to do everything. You got to learn a little bit about reading this dashboard. You know, what does that big green N mean? Well, it means you're neutral. Okay, what does that big flashing red light mean about the temperature? Okay, we're running a little bit hot. Some of the gauges, you know, how fast are we going? How much gas, which you might equate that to petrol consumption is like CPU consumption. And just understanding these things at a high level. Again, not a system programmer, don't need to be a system programmer. But you got to know a little bit about how the environment operates. And if you have good tools, it's easier and easier to find those things out than it used to be in what we call the bad old days. So let's just talk a little bit about human nature. We hate to wait. That little colored guy on the right, my wife calls that the beach ball of death. She'll occasionally come in here if her Mac has got the beach ball and say, "Hey, performance guy, you know what's going on? My Mac is slow. Help." Of course, I tell her never trust a computer you can lift. That's not very satisfying. But this is really, besides the economic aspect of the performance role, which is what the executives want, right? You're running efficiently, you're keeping resource consumption under control, not being wasteful with this what I call a premium server, which is what the mainframe is, but also your applications. You think about a grocery store and you have a series of checkouts. Let's pretend for this argument that we don't have self-checkouts. Well, if you own that store and you have someone running every checkout, maybe you have 20 checkouts, well, you're unlikely to have any lineups at all. But it also means then you have to pay those 20 people. Whereas conversely, if you only open one checkout, well, maybe you're saving in your costs and your salary because you're only paying one person, but you're going to have big lineups and some people might even leave. So it really gets back to that balancing act, which is what the role is all about, which means you got to understand a little bit about what creates these lineups, how they work. And you don't need to be a detailed mathematician, but you do got to know a little bit about queuing theory, which is what I like to simply call the mathematical study of waiting. And as I kind of described, think that grocery store, your business, your resources are too low, which means you don't have enough checkouts open, then your queues are going to be too long. People are going to leave the store. You're going to lose money. If they're more than required, sure, you can, as we call, throw hardware at the problem. This application is slow. Guess what? You can buy a new Z17 with 50 cores in it. Guess what? That application is going to do just fine if you can afford to do that. Not every site can. The goal is really about finding the right balance. Now, no discussion of queuing theory would be appropriate without mentioning Dr. John Little, who left us just last September. This gentleman was well into his 90s and gave us what you see before you, what is known as Little's Law. Just a little bit of background to share. Dr. Little did not actually invent this formula. It had been around for a while in the 50s. It was used by lots of mathematician capacity. If you think about it, you know, you're not just in computing, but if you were designing a highway, you know, how many lanes do I need based on how much traffic, you know, the grocery store analogy, anything like that is where this type of math comes in handy. You can see what it's allowing you to calculate. It's allowing you to calculate concurrency and arrival rate and time in the system. So, you know, how long things will take to move through a system. Even if you just stood outside a store and said, you know, what's the rate of people entering the store and what's the rate of people coming out, give you an idea of how efficient that system is. But Dr. Little wrote the paper in 1961 and it was approved first time around. So since then, we give him the honor of calling this Little's Law. Now, we can measure this. The original formula in front of you calculates how many people are in the system by simply multiplying the rate of people joining the line. We call that the arrival rate, or technically is actually the amount of time in between two consecutive arrivals. This is on average, of course, versus how long are they here. But being an equation, of course, I can switch the values around pretty easily, right? So I could say, well, maybe I want to calculate the rate of people joining the line. And well, to do that, I would take the total number of people in the system on average versus how long are they here on average. Once again, notice I keep repeating that average. This always works on average. Of course, you can always have first arrivals and things like that. But probably the third one is the most useful. How long will I be here? I want to know, I have an appointment or something like that, and I'm waiting, or maybe I'm just joining the line and I'm looking at, oh no, this looks busy. I don't know, when am I going to get out of here? And all that is the average number of people in the system divided by the rate of people joining the line. Well, let's apply that, shall we? Have any of you ever been in this situation? A lot of us are probably in this situation every morning if you drive to a normal job. But imagine if you are just sitting, and you're literally sitting, you're not moving, you don't really have anything to do. And it occurs to me that, well, maybe if we understood a little bit about what was leading to this, say you just need to get to that next exit. You're not moving, and you've got an appointment, and someone's calling you and saying, when are you going to be here? And your first instinct is, well, I don't know. I'm not moving. I'm sitting in traffic. I have no idea when I'm going to be here. Well, let's, for fun, if you want to play along, do a little bit of back of the envelope math here. How many cars are in this system? I'll call it right now. Now, I haven't counted these, but if I, just for fun, it looks like there's about 6 lanes wide, and maybe going up to that next exit, let's say 20. So 6 times 20, so it's 120 cars, let's say, in our little system between us and that exit. 120 cars are in this system. Okay. What about the arrival rate? Now, if I'm on the ramp, some highways have these little metered lights. See the little red light there, and it'll turn green and let a few people on at a time. This is to, prevent the system from becoming too overloaded. It's kind of a neat little metering system. So let's say, just for argument's sake, that light turns green every 10 seconds. And there's 2 lanes, so every 10 seconds, 2 cars get to go. So if that's 2 cars every 10 seconds, that's 12 cars per minute. 12 cars per minute are joining that system that we looked at in the last slide. And one of the things I point out here about these rates are, whenever you're applying Little's law in any way, is that it's critical that you use the same unit. Doesn't matter which one. I've got here per second, per minute, per hour. You can use any of those. Just don't mix them. If you're talking about occupancy in a certain value, you're talking about how many people are in there, you're talking about arrival rates, you want to consistently use the same value. In this case, we're doing it per minute, and then your result will be at that same value. So any guesses? Oh, I just looked at the people on Jim Horns here, and Jim knows, so you're not allowed to answer, Jim. So there. That's all right. Good fun. What did I say? Remember, was total cars in the system divided by the arrival rate of 12 cars per minute. 10 minutes. On average, if I'm sitting at that car at the back and I want to get to that next exit, I'm going to be around 10 minutes. I can tell the person on the phone that I think I'm going to be there in around 10 minutes. And why does that work? You say, but wait a minute, I'm not moving. I don't understand. Well, how that works is we're doing this per minute, and we notice that we have an arrival rate of 12 cars per minute. Well, if I'm adding 12 cars per minute, but the average is 120, that means the average is not growing. That means clearly cars must be leaving the system as well, or the occupancy value would grow. So just a little bit of interesting fun that you could maybe use in your real life. One other little bit of fun. No wrong answers here. And I apologize, it's sometimes more fun when you're interactive. People can shout out what they think. Any guesses about whether 3 lines are better? The line on the left, I sometimes call this the Costco chaos line, or the McDonald's line, where maybe you're in one side and then you're like, oh, that looks like it's moving faster, that looks like it's shorter, and you kind of jump around. It's human intuition, right? We're looking for the shortest line. We're like, that looks like it's moving faster. That checkout person looks like they're quicker. Okay. Versus the one on the right, it's like the bank line. One single queue. Wow, that looks really long. I don't like that. Well, I can tell you on average, the one that looks really long on the right, on average, is going to be faster. And one of the main reasons for that is you've got these 3, we'll call them servers, right? The checkouts there in green. And on the left, if one of those breaks, like if you're in the McDonald's line, you suddenly get to the front and you go, ha, I passed that guy ahead of me. Look, I'm next. I get to get my Big Mac now. And then, oh, it's shift change. Oh, no, sorry. I have to take out all the receipts and take the cash drawer out. Now somebody else, and you're not moving. It's stopped. You're not going anywhere. So if one of those breaks on the left, that line completely stops. Whereas on the right, as long as one of them is operating, the line never stops. It might slow down because I only have 2 active servers instead of 3, but it will always continue moving unless all 3 stop. The other thing about the line on the right, it's democratic. First in, first out. Whoever was the next in line will be the next person served. Whereas on the left, you can kind of jog and then maybe you get ahead, or maybe you're behind and you feel like, well, this isn't fair. I got here before that person. I should be served next. So that's why we like the one on the right. Let's talk about utilization. Hey, like anyone, sometimes let's just ask Google. So I Googled, I was kind of surprised with this answer. Utilization, primary method by which asset performance is measured and business success determined. I really did not expect that answer. I was surprised. Oh, wow, this is like a financial kind of definition. That's interesting. To turn to profitable account. Of course, maybe that explains why my boss used to say a busy CPU is a happy CPU. Interesting. Okay. So I Google CPU utilization. Okay, this makes more sense to me. This is kind of the answer I expected, referring to a computer's usage of processing resources or the amount of work handled by a CPU. Resources. Remember back to our definition, this is half of the job. What are the resources that are being consumed? Again, we're not talking about the inexpensive commodity servers. We're talking about the premium, Z mainframe environment. This stuff, I'm reluctant to say expensive because it already has that bad rap, but it's a premium server. Why? Because it can do a lot more work than commodity servers. But you want to keep track of these resources and what I'm consuming. But you also want to consider when you talk about how busy, the boss will say this every day, right? Well, how busy is the machine? Well, you want to consider the average across time, Lisa, logical versus physical, or average across multiple components. So the average across time. If you look at these 2 light bulbs, the one on the left by itself is 0% busy because it's off. One on the right is 100% busy because it's on. If you put them together, you might say, well, collectively, on average, they're 50% busy if you think of it as one unit. And that's the way a CPU works. It's either in use or it's not. What you're really tracking with utilization here is measure of usage over time. So 80% busy simply means it's in use, or 100% busy, the light is on, for 80% of the time, and not in use for 20% of the time. That's all that means when you translate that. When you look at logical versus physical, if you get a little bit into some of these metrics, how busy is the machine today? Well, it depends. Another one of those universal answers. There's MVS busy, there's LPAR busy, there's average KEC busy. There's lots of different metrics, and depending on how they're averaged out, and if you're looking at individual components or an average of the whole machine or the LPAR, have different perspectives. And you kind of want to know all of these to have an idea, because at the end of the day, they're going to affect how your applications perform. If you do use these, I'll tell you just off the top of my head, I like to think of MVS busy and LPAR busy as supply and demand. So MVS busy is like the demand from the LPAR, what it wants. LPAR busy is what the machine is delivering to it. Most of the time you see one line here because they're overlapping. Supply and demand are matching. Occasionally you see these little red spikes on the right. What that means is the LPAR wants more than it's getting. LPAR busy being lower than MVS busy, mean it's not, the machine is not delivering everything it's asked for. Why? We have a shared environment. Other LPARs get a minimum fair share as well. And if those LPARs demand their share and the machine overall starts to get busy, then you're starting to essentially make those business choices again about, well, who's going to wait and who's not going to wait. And you think about average across components. So say one CPU dispatch for 900 seconds in a 900-second RMF interval. That's 15 minutes, pretty standard interval. And a second CPU dispatch for 450 seconds at the same time. So the first one would be 100% busy, second one would be 50% busy. Let's say in another scenario, those same two CPUs are each dispatched for 675 seconds. So in that case, each CPU is 75% busy. Well, on average, if the machines in both cases are 75% busy, but will performance be equal? They're very different profiles. This is just yet another thing you need to consider. And there's no black and white answer to that. It's really a lot of understanding your applications. Is your application one of these multi-threading, or is it more dependent on a single core? Or two lanes is kind of tight as well. You know, is that enough? Maybe you want to consider having more cores but slower. There's that debate that you can go on and on into. Got to keep moving here. I'm not going to make it. Capacity. Capacity is like the size of the parking lot, and obviously that can vary. So you can have a 10 space lot in a little shop that has 5 spaces use, or you can have a 10,000 space lot with 5,000 spaces use. In both cases, they're 50% utilized, but obviously that larger lot has a lot more capacity. What if that highway or that store is full? If your occupancy space is not unlimited, which is the same with our capacity, unless we want to keep adding and adding and adding, then occupancy expressed as a percentage is your utilization. So this is the mall parking lot at Christmas. It gets busier. The rate that our cars are entering the parking lot, just like original highway before, is increased, but the number of spots is fixed. There's not more of them. So the length of time to get in and out is going to increase. And that has nothing to do with your skill as a driver. If there's lots of empty spots, you can just drive in. But if you're spending time driving around, well, your overall parking time, response time, will increase, even though it's not like you're driving differently. You're just impeded. So consider these examples. From 50 to 60% busy, an increase of 10%. I've got 500 spots free out of my 1,000, probably not going to be waiting. I go down to 400 spots free. I probably don't even notice. I'm still going to get a spot pretty quickly, even though I had a 10% increase in utilization. Versus 89 to 99%, 10% increase as well. But at that higher level utilization, I've got 100 spots free. I'll probably get lucky. I probably won't wait too long. Whereas I go down to 10 out of 1,000 spots, I've only got 10 spots free. Now I'm going to be driving around for a long time. Now my overall response time is going to be significantly longer at that level of utilization, even though I still know how to park. I'm not driving any slower. I'm just impeded. Both of those situations, like the other example, increase by 10%, but the response times are going to be dramatically different. This is why you don't want to run at 100% is a short answer. And that may be going back to that definition of utilization about profitable value. Boss saying, hey, we're only running at 98%. Throw more load at this machine. That's really not a good idea, because what you're doing is, your more smoke is going up the chimney if you look at it from that analogy, as opposed to being delivered to the applications. You're spending more and more time driving around. In our parking lot analogy, the service time at the bottom, that little blue, that's how long it takes you to pull into a spot. You can do that in the same few seconds every single time if no one's in your way. That queue time is all the cars that are in your way, all the spots that are full that you keep driving around and around trying to find an empty one. I just want to talk briefly about years ago at CMG, we had the CIO from Netflix that visited us, and it was a really interesting talk. Netflix, of course, doesn't run on the mainframe. They run in the cloud, virtual commodity servers. And he told us on any given night when people start watching TV, they will allocate in a virtual cloud kind of perspective, more than a data center's worth of capacity. And I thought, that's really, really interesting, really, really cool. But you would not do that in a mainframe environment. It's not that you couldn't. You could say, well, let's have AI automatically turn on cores every time applications get slow. You're not going to do this for very long because your expenses are going to go through the roof. The same rules, the same lessons or guidelines that you would use in a cloud or commodity server environment really don't make sense in the mainframe. This is the other reason this particular role that I'm talking about is extremely useful in our environment, because you don't want to just automate. You can turn cores on, but it's a business decision. It's an expensive business decision requiring some analysis and business decision to be made. Okay, 10 minutes are going to make it. You're taking a road trip. You drive to your mom's house and looking at these little picture, what's my average speed? Well, I could say, well, what time did I leave and what time did I arrive? And I know how far it is, so I could just say, well, calculate a single number for the average speed. But of course, I'm going different speeds on different parts of the route. There'll be parts where I'm just sitting at a stoplight, so my average speed is 0. And there'll be parts where, maybe on the highway, maybe I'm doing 100 kilometers an hour. So, you want to kind of break down that, we call it the distribution. You do the same thing when you're analyzing response time of a transaction. What's the distribution? Where is it spending its time? Am I spending my time waiting for CPU, or am I spending time waiting for IO? If I'm waiting for IO, then that's an example where, well, adding more CPU won't actually help. So you don't necessarily want to do that. These are a lot of the types of things that you gotta understand just conceptually. And again, we're not talking about heavy math here. Just step back and maybe resist that automatic instinct. Well, this application's slow. Clearly, we need to increase priority, or clearly we need to just add resources. Figure out where it's spending its time and figure out what variables that you can control. And that applies to priority. I've got this little notepad on my desk every day. Plan of attack, most critical, must get done. Would be nice, not a chance. And completed or retreated. Maybe it didn't get done. Ask the application owners, is your application important? What do you think they're going to say? Of course they are. They're all going to say it's important. Now, the mainframe, as it says here, scales better than any platform. And while these resources are certainly vast, they're not free, they're not unlimited. So you really want to resist that urge to say, well, this application is complaining, I'll just give them number 1. This application is complaining, I'll give them number 1. You can, but what workload manager is going to do and say, well, okay, I'm going to try and do what you're asking you to do, which means I can't sacrifice anybody when I get too busy, which means it's going to thrash and no one's going to get done. Everyone's going to get a little slice, but no one's going to actually get done. It's extremely inefficient. You have to make hard choices about who's really important. And this gets back to being that judge. Okay. Ooh, I think I'm going to make it. So this is the role, and it gets back to that shared ecosystem that I mentioned. My friend Dave Hutton described this once as a swimming pool. So your application may very well be doing the same thing. The owner might say, look, I didn't change my code. I didn't do anything. How come I'm slow? Well, maybe there's somebody beside you splashing you. That can happen. And your role as the performance analyst is to be that lifeguard to ensure that everyone thrives in the giant Z pool in the mainframe environment, not just favoring given applications. That doesn't mean you can't have loved ones, which is another great Ray Wicks quote. He came up with the term loved ones. But it really is all about balance. I know I'm right up against the clock. My last slide here is just about the economics of it. I really do believe these intersect. Application performance versus resource consumption versus cost, customer experience, company success. All of these, performance is kind of really at the center of this. If the mainframe was a car, you could not perform basic maintenance or change the oil for a year and it would still run. But that doesn't mean it's a good idea. It'll run less efficiently. It will consume more resources. So to really maintain that peak efficiency, it requires specialized care and feeding, which is what we do as performance analysts. I think I'm right up against the clock, Elisa. Is there any questions or did I make it?
Yeah, we have 2 minutes until the top of the hour. So if anyone have any questions, feel free to ask. I will unmute you or ask in the chat.
There's a great quote from American economist Thomas Sowell. He describes economics as the allocation of scarce resources which have alternative uses. And time is literally the scarcest of resources. So I guess I would just say thank you for allocating your scarce resources this morning.
Well, thank you so much. All I want to say is you make a great teacher. I've always said that whoever can give a very good example from real life, so even the children can understand, makes a great teacher. So thank you so much. Thank you for your time. Thank you to the attendees. And well, if no more questions, feel free to join
Thanks,
our
everyone.
other sessions.
Yeah, that QR code is correct. So
Yes.
you can scan that or the session code.
Yes,
And
please give your feedback.
thanks, everyone.
Thank you. Bye.